Final basic structure theory of Lie groups and Lie algebra to be delivered by Dr. Samir Hazra from GITAM University. He will continue from his previous talk on the Tuesday. Over to you, Samir.
Yeah, thanks, Devendra. So basically, before this lecture, we have already done this root system. Okay. So in rank 2, we wrote down all the root systems here. So they turn out to be only 4. Okay. So how did we get to those root systems? So basically, how did we draw those pictures basically? So we had one base inside phi, and the elements inside this delta, we call them simple roots, and this base has some properties. Okay, and this cardinality of the base is definitely this dimension of E, which is nothing but the rank of phi. And one root system can be called reduced or reducible if we can write phi as phi 1 union phi 2 with phi 1 inner product phi 2 equal to 0. So basically, they are orthogonal subsets of phi. So if we cannot break them into orthogonal subsets, then phi is called irreducible. And from a root system phi, we can actually write a matrix which was called the Cartan matrix. This is the entries are Aij. How do we get that? So basically, we fix an ordering. So suppose this is delta, which is the base. There are some roots here, let's say L many, and then we give them an order. So suppose this alpha 1, alpha 2, alpha L, this order is fixed. Then if we collect these integers alpha I, alpha j, and write them in the ith, jth entry of the matrix, we get a matrix called Cartan matrix. Of course, these numbers alpha I, alpha j, they are integers. Therefore, the entries of the Cartan matrix are all integers. So Cartan matrix is an integer matrix. Okay, so we have also seen this, that Cartan matrix of a root system determines phi up to isomorphism, which means what? So basically, if you have two different root systems having the same Cartan matrix, okay, then those two root systems are actually isomorphic root systems. There are some properties of the Cartan basically entries of the Cartan matrix. So all the diagonal AII must be 2. If I not equal to j, so basically off diagonal elements must be either 0 or -1 or -2 or -3. And if Aij is somehow 0, then Aji must be 0, and Aij, if it is a -2 or -3, so once there is a -2 or -3, then Aji is -1. So opposite to that entry will be -1. Well, so basically we started with a semi-simple Lie algebra, this one, and H was a Cartan subalgebra, and from there we could find a Euclidean space and then a root system inside that. From the root system, we wrote a base for that, and actually this always exists. So basically, theorem here is that this exists always. This is the theorem. There is a theorem, and from the base, after fixing an order, so fix ordering, we get a matrix called Cartan matrix. And from the Cartan matrix, we want to see which are linking diagrams. We can actually draw some diagrams using these Cartan matrices. Okay. So suppose this is the base and ordering is alpha 1 to alpha L. Then these are the entries. So these are given by actually alpha alpha j. They are given by 2 alpha alpha j over alpha j. Now it is of course clear that if we change the ordering, here, then we'll get a different Cartan matrix, but we regard them to be equivalent. They are called equivalent Cartan matrix because if we just change the ordering of the base elements here, alpha 1, alpha L, then we are not affecting the root system at all. So basically, the root systems remain unchanged, right? So under this change of ordering, And therefore, if change of order gives some other Cartan matrix, we'll call them equivalent. Now, suppose we have an isomorphism between root systems. Okay, so if this is the base, delta is the base in phi, then via psi, we can actually write a base for phi dash, which is given by this psi alpha 1, psi alpha. So basically, psi acted on the applied on the base elements. Then we remember that these are the entries of the Cartan matrix for phi dash. So basically, Aij dash, which are nothing but psi alpha I, psi alpha j, which are again nothing but alpha I, alpha j, which are again Aij, right? So basically, if all the corresponding entries are same, if all the corresponding entries are same, then phi must be isomorphic. Right? And so basically, from phi, from root system, we can get a Cartan matrix. And if two root systems has two root systems, they have the same Cartan matrix, then they are isomorphic. So basically, we have a bijection between root systems and Cartan matrices. So for example, if we want to see SL2, this is generated by this H100-1 diagonal 0100 Y0010. So the Cartan here is span of H, which is this. And here we can see that add H is actually semisimple. Therefore, H is semisimple. Therefore, H is inside the Cartan. Now, it cannot have two-dimensional Cartan for obvious reasons. So this is the maximal total subalgebra or Cartan subalgebra. And how many roots are there? So basically, H is one-dimensional, and we know that the base has dimension of H number of elements. So dimension of H is 1, so base has only one element, which is alpha. Then the root system is just alpha minus alpha. There cannot be anything else. So if we want to draw the roots alpha and minus alpha, so basically if this is alpha, then this must be minus alpha. So this is the root system in picture. Okay. So this is a rank 1 system because rank is what? Rank of the root system is cardinality of the base. So cardinality of base is 1 here, and therefore rank of phi is just 1. Well, so if I want to write the Cartan matrix in this example of SL2, then we have only one element in the base, so there is no ordering possible. So this is the only element, which is alpha alpha, and then if we calculate this is nothing but by formula. So basically by definition, 2 alpha alpha by alpha alpha, which is nothing but 2. So all these are 1 cross 1 matrices. Okay. And if rank phi equal to 2, so this was the rank phi equal to 1 case. And if rank phi equal to 2, whether we can write all the Cartan matrices, let us see. So if rank phi equal to 2, then the matrices are all 2 cross 2. So these are all 2 cross 2 matrices. And diagonal, like AII must be 2 always, because for simple reason, AII is just 2 alpha I over alpha I. So that's nothing but 2. So diagonal elements are always 2, 2, right? And then what are the other entries of non-diagonal elements? Non-diagonal elements can be 0, -1, -2, -3 with subject to these conditions, these two conditions. So if I go there, we can write 0 here, but Aij equal to 0 implies Aji is also 0. So this 0 means this must also be 0. If this is -1, this can also be -1. Okay. If this is -2, this has to be -1 because we have seen that. And if this is -3, this also has to be -1. Now we can also write this. So basically -2 and -1, right? Sorry. Here I would like to write -1, -2. Otherwise they are same. -2, -1, and -2. Okay. Similarly, here -1, -3. So basically -1, -1, -1, -2, -1, -3. But suppose this matrix is written in this order, alpha 1, alpha 2, in this order. So if we just change the order of elements in alpha 1, alpha 2, then we get this matrix actually. So basically, thus just a change of ordering in the base elements in the simple root actually gives this. So they are actually considered to be equivalent, because we have seen if ordering a different order gives some Cartan matrix, then there is Cartan matrix equivalent. Similarly here, if this is written with respect to alpha 1, alpha 2, this ordering, then this is given by just the reverse ordering alpha 2, alpha 1. So basically these are also equivalent. Similarly, this and this, they are equivalent. So you see that there is no more possibilities, and therefore these are the only Cartan matrices. Okay, so there are only 4 Cartan matrices, 4 different Cartan matrices of rank 2 root system. So this is no accident. Basically, we have seen that in rank 2 there are only these 4 possibilities. So it is obvious that we shall get only 4 different Cartan matrices like I got there. So now we want to classify the Cartan matrices. So rank 5, one case is done in example. Rank 5 2 is done right now. But what about rank 5, which is bigger than or equal to 3? So basically large rank. So suppose base has this L many elements, so L simple roots. Then Aij is of course alpha I, alpha j. So it is difficult to write all possible Cartan matrices of order L cross L. So because here the Cartan matrix will be of L cross L order, right? Cartan is of L cross L order Cartan matrix. It's not an easy task to write all the Cartan matrices of order L. So actually, therefore, we try to assign diagrams to root systems. Okay, so some graphs or diagrams, they are called coaxial graph of phi, okay, of the root system phi. So what is it? This coaxial graph is actually a graph with L many vertices. So L is what? L is the number of simple roots in the base. L vertices, and where are the edges? We must need to know. For I not equal to j, so if we have 2 different vertices, the number of edges between ith and jth node or ith and jth vertices is actually nij, which is given by this formula, aij equal to aji. And if we check what are the possible values of aij times aji, we'll see that there are only possibility of 0, 1, 2, 3. So basically, if aij is -1, aji can be -1. If aij is -2, -3, then aji is -1. aij is 0 implies aji is 0. So aij equal to -1, aji equal to -1. It can also be -2, -3. But in all these cases, aij, aji cannot be outside this. Okay, and also they do happen 0, 1, 2, 3. They do happen. From this we can check. So aij, aji is what? Is the number of edges between ith and jth nodes or ith and jth vertices. So that is denoted by nij. Okay. So now let us try to draw some Dynkin diagrams. Sorry, Coxeter graph. We have not arrived at Dynkin diagram now. So Coxeter graph for rank 2. So rank 2 matrices are this up to equivalence. Okay. So suppose this is the Cartan matrix. Okay. Then we want to draw the Coxeter graph for this. So in the Coxeter graph, there are L vertices. We've seen L vertices when L is the number of simple roots. So L is the cardinality of base. And in this case, cardinality of base must be what? Must be 2. So there are 2 vertices. Okay. So let's say alpha 1, alpha 2. 2 simple roots. So 2 vertices. And how many edges are there between alpha 1 and alpha 2? So it's clear that A12 times A21 is 0. So this is the element A12, entry A12, and this is A21. Their product is 0, right? So this implies N12 is 0. So basically, between first and second vertices, there is no edge, and therefore there is no edge, right? Similarly, for this, A12 is -1, A21 is -1. So A12 times A21 is 1, which is nothing but n1, 2, right? So basically between first and second vertex, and there are only two, there is only one edge. So this is one edge. Similarly here, this is a12, this is a21. So Nij here is basically in 2 cross 2 case, it is just the product of diagonal entries. So -1 into -2 is 2. Similarly here, -1 into -3, which is, so basically Ni, not Nij, n12. n12 is 3 and n12 is also 3, though these are two different matrices. Okay, we have seen that they are equivalent. Okay, and the observation that their coexeter graphs are same tells us that the coexeter graph cannot determine the Cartan matrix. For example, if this this coexeter graph is given, they are same. There's the same graph. Okay, two vertices and three edges in between them. So we cannot decide which one to write, right? So because both of them correspond to these two. So basically these correspond to both of these matrices. So how to decide? Well, so therefore we need to introduce Dennkin diagram. So for example, we can see here another example. So if we have this matrix, then we can draw this diagram. And if we have this matrix, these are different matrix, we have this diagram. Again, coexeter graph actually. Coexeter graph. So for these two different matrices, we get the same coexeter graph, right? Okay. And here we make the observation that the number of edges Nij between alpha j, if more than 1, so for example, in between these two vertices, let's say alpha 2, alpha 3. So in this case, n2, 3. So second and third vertices, the edges, there are only 2, right? So n2, 3, 2. Similarly here, n2, 3 equal to 2. Okay. So these observation tells us that if the number of edges Nij between alpha and alpha j is more than 1, then norm of alpha I is not equal to norm of alpha j. Okay. So why is that? So suppose Nij, which is more than 1, right? More than 1. Nij is more than 1. So there are double or triple edges between alpha I and alpha j. So you want to prove that norm of alpha is not equal to norm of alpha j. So Aij dot Aji, which is nothing but Nij, and this is again alpha I alpha j and alpha j alpha I, which is either 2 or 3. Well, so alpha I alpha j, what are the possibilities? Or Aij, what are the possibilities? If we remember, for Aij, for any ij, the only possibilities are 0, -1, -2, -3. Okay, so this is the only possibility for Aij. Then if alpha, so basically this Aij, Aji, if their product is 2, then definitely this is not equal to this. So from here, how can we get 2? So basically -1 into -2 or -2 into -1. So in particular, they are not same. So that's what we have written here. Similarly for 3, if the product of these two numbers is 3, then how can we get 3 from these four numbers? So basically -1 times -3 or -3 times -1. Again, always alpha I alpha j. So the numbers are not equal, that's all. So this number is not equal to this. But by definition, this number is 2 alpha I alpha j over alpha j. And this number is 2 alpha j alpha I over alpha I. So if they are not equal, then what can we write? So this implies that norm of alpha j is not equal to norm of alpha I. Why? Because this alpha I alpha j and alpha j alpha I, they are the same numbers. Okay, because this form, this bilinear form on the Euclidean space is actually symmetric. So therefore, alpha I alpha j and alpha j alpha j, they are same, and therefore norm of alpha j is not equal to norm of alpha I. So without loss of generality, we can take that norm of alpha is bigger than norm of alpha j. So these are same quantities, the numerator, they are the same quantities. Only difference is in the denominator. Okay, so if norm of alpha I means this one, if norm of alpha is bigger, then this denominator is bigger than this denominator, which means this number must be less. What was it? This is AJI from here. AJI. So AJI must be less than AIJ. So in the matrix, we can easily see which one is bigger. Modulus of AIJ is bigger or modulus of AJI is bigger. So if modulus of AIJ is bigger, then norm of alpha I is bigger than norm of alpha j. And whenever actually norm of alpha I is bigger than norm of alpha j, okay, so in some sense we can say that this is longer than this. Okay, so then call it long and call it short. That's all, because norm of this is bigger than norm of this. And then in the Coxeter diagram or Coxeter graph, you put an arrow from long to short. Like here, if norm of alpha I is bigger than norm of alpha j, so basically if alpha is the long and alpha j is the short root, then from long to short you put an arrow. Similarly here, even if there are 3 edges, you can put this arrow. So this we do only when we put an arrow only when the number of edges is either 2 or 3. Okay, so let us check what we get. So Coxeter graph with appropriate arrows. Appropriate arrows means what? If norm of alpha is bigger than norm of alpha j, then alpha I to alpha j, we put this arrow. That's all. We put this arrow. So after putting all these appropriate arrows from the Coxeter graph, whatever we get is called Dynkin diagram of the root system. Okay. So in some cases, arrow does not matter. So for example, if there are only 2 vertices, so like this, I mean, this is also an example. So if there are only 2 vertices, if we even don't put arrow, or even if we put the arrow in different direction, they are same, because from this graph to this graph, there is a graph isomorphism. So they are necessarily the same diagram or same graph. Okay. But in this case, for example, so there are 3 roots now, alpha 1, alpha 2, alpha 3. So if it is alpha 1, alpha 2, and alpha 3, we cannot have, or without even any name. So this graph cannot be made into this graph by graph isomorphism. Okay, so obvious to see. So therefore, arrows or arrow here matters. Okay, this arrow matter. And in this case, when there are 2 vertices only, the arrow doesn't matter, because whichever way you draw the arrow, they are the same object. So now, what happens to this Dynkin diagram? So basically, these are called Dynkin diagrams. On the Coxeter graph, you are putting arrows according to this rule. Okay. So from long to short. So now, what happens to the Dynkin diagrams when phi is not irreducible, which means phi is reducible. So if phi is reducible, we can actually write phi as a union of phi 1 and phi 2 with this orthogonality condition. So phi is a union of phi 1 and phi 2, of course disjoint, with this orthogonality condition. Then equivalently, this is actually if and only if, I can prove this, it's very easy to see. Then base, the simple roots can also be written in 2 disjoint union of at least 2 collections. Okay, so collection 1, collection 2, and this is a disjoint union. If phi is reducible, then only we can do that. Again, with this orthogonality condition that delta 1, delta 2, their inner product is 0. So now suppose this is the case, phi is not reducible. We can write the base as a disjoint union of simple roots with this orthogonality conditions. Now take alpha I from the first collection and alpha j from the second collection. Since this orthogonality condition holds, alpha I, alpha j, when alpha is from the first collection, alpha j in the second collection, it must be equal to 0, because the orthogonality condition is there. And now what is alpha I, alpha j? This is nothing but Aij, which is the ijth entry in the Cartan matrix. and that entry must be 0. And if Aij is 0, we know that Aji must also be 0. Then what is Nij, right? So if Aij is 0 and Aji is 0, what is Nij? So basically, Nij in this case of a reducible root system, Nij is Aij, Aji equal to 0. Okay. So in picture, if we take this to be the first collection and this to be second collection, we know that since this is reducible, we took this them to be orthogonal, right? And since they're orthogonal, if any node is here and any node is here, Nij is actually 0. Therefore, there is no edges. So 0 number of edges, right? So there is no edge between these two. So then what happens is that there is no connection from these vertices, from any of these vertices to any of these vertices. So Dentin diagram becomes disconnected. Okay. So now if we completely reduce the root system, the base. So basically this is the base for the root system. And we completely reduce it, which means we write it as a disjoint orthogonal union of m number of subcollections. And suppose that all these are irreducible. So basically we cannot decompose this into two more subcollections. Okay. So suppose all these are irreducible and we have the orthogonal constant delta j equal to 0 for I not equal to j. Okay. Then from here we can actually get a decomposition of phi. These are equivalent things. So the root system then can be written as a union like this, phi 1 up to phi m, where phi I is nothing but the span of delta I. Okay. So phi I is the span of the base delta I. And since phi i's are all disjoint, okay, this ei and of course orthogonal, they are also orthogonal. Phi I, phi j is 0 for I not equal to j. Okay. So then E can be written, the actual Euclidean space can be written as an orthogonal direct sum of this form summation I to j ei. Okay. So then what happens is that phi I, which was span of delta I, and ei, so is an irreducible root system. So basically, then the Dynkin diagram, what happens to the Dynkin diagram? And Dynkin diagram of each of these components is connected because this is irreducible. Okay, and from there we get this idea that if we classify the irreducible root systems, we are done. So basically, if we classify the irreducible, actually is equivalent to classifying the connected Dynkin diagrams, right? So if Dynkin diagram is not connected, obviously the root system is irreducible, and vice versa actually. So better to focus on the irreducible root systems and thereby equivalently focusing on the connected Dynkin diagrams. So from here we can write this theorem. If phi is an irreducible root system of rank L, then the Dynkin diagram is one of the following. Okay. So basically, we are trying to write all possible Dynkin diagrams which can happen to be a Dynkin diagram of some irreducible root system. So if phi is any root system, then its Dynkin diagram, irreducible root system, then its Dynkin diagram is one of these. Okay. So there are 4 infinite classes. These are infinite families. And there are 5 more here. There are only 1. So E6, E7, E8, only 1, 1, 1, and F4, G2. Okay. And these are infinite families. So there is also a restriction on L. So here L can be bigger than or equal to 1, L bigger than or equal to 2, bigger than or equal to 3, and bigger than or equal to 4. So why this is to avoid any duplications between, so basically among them. For example, if I, so we are removing D3, right? So DL, L bigger equal 4, which means we are removing D3. So we don't want D3. So D3 must be somewhere. So what is D3? If we want to draw, so this L is the number of nodes, right? So D3 means this, and this, okay? So there is no but then this is nothing but, this is same as this, which is A2, A3. So D3 is nothing but A3. Okay. Similarly, so for example, why we don't include E5? Okay. Only E6 is there. E6, E7, E8 there, but E5 is not there. So for example, if we want to draw E5, what it is? So in the similar fashion, we can draw this. This is E5, but this is nothing but D5. So E5 is actually D5. What is D5? Like 3 here. So from here we can see. So actually this is same as this. They're same graph, right? And this is D5. So E5 is D5. So that's how. That's why we need to restrict some else and so on. And the theorem says, so it's a big theorem, and its proof is also done in multiple steps, and therefore it is out of scope. So it says, if we have any irreducible root system, so start with any irreducible root system. So start with any irreducible root system phi, and if you do the Dynkin diagram, the Dynkin diagram must be one of these. But this doesn't guarantee that for any of these diagrams there exists a root system, okay, for which this is the Dynkin diagram. So this does not talk about existence. So now, once we have the Dynkin diagrams, whether we can write the Cartan matrices from Dynkin diagram, okay. So this can be done very easily. So suppose this is, so this is not Dynkin diagram because we need one arrow here, since this is double edge. So suppose this is the arrow, or one could give arrow in this direction, sorry. So double edge, this. Okay. So they are essentially the same. So if we want to write the Cartan matrix out of this, one can very easily write. So Cartan matrix means the diagonals are all 2. Okay. So this is the 2, 1. This is the 2, 1 entry. Okay. So so vertex, sorry, this is the 1, 2 entry. So vertex 1, and how many edges in between 1 and 2? There is only 1. So the only possibility is -1, -1, and then 2. So basically, number of edges Nij, remember, Nij is product of Aij, Aj. So this is what? This is A12, and this is A21. So A12 times A21 must be the number of edges. So between 1 and 2, right? So let's say this is 1, this is 2, this is 3, this is 4. So then A12 is the A12 times A21 is the number of edges between 1 and 2. So similarly here it is A13. So there is no edge between 1 and 3. So this must be 0. Similarly, between 1 and 4 there is no edge. This must be 0. Okay. So 2, 1 is done. 2, 2 must be 2 because it's a diagonal. 2, 3. 2, 3, there are 2 edges. So product of this entry, product of this entry, and product of this entry must be 2. But which one is what, right? So we have seen in previous slide that not exactly previous, but okay. So if mod of Aij is bigger than mod of Aj, then alpha I, norm of alpha I is bigger than norm of alpha j. So here, this is alpha 2, this is alpha 2, and this is alpha 3. This arrow means alpha 2 is bigger. This arrow means alpha 2 is bigger. So in this case, so this is basically alpha 2. So alpha 2 is long. alpha 2 is long. Let me write alpha 2 long and alpha 3 short. Okay. So if alpha 2 is long, which means mod of alpha 2, this means, norm of alpha 2 is bigger than norm of alpha 3. Which means what? Which means from here, mod of A to 3 is bigger than mod of A 3 2. So now since there are two edges, product of these two entries is 2 and individually they are negative, and mod of A23 must be bigger than A32. So this is the 2-3 entry and this is the 3-2 entry. So this mod must be bigger. So this must be -2, only one option left. And this must be -1, -2, -1. And again, I'll write 2 here. And this position is 3, 1. Okay, so actually, if this is 0, we can directly write this to be 0 because Aij is 0 if and only if Aj is 0. And since this is 0, we can also write 0 here. Okay, what is this position? Let's say 3, 2, 4. 2, 4, there is nothing. So this must be 0. And this is 3, 4. 3, 4, there is one edge. The only possibility is -1 and -1 here, right? 3, 4, and this is the diagonal. It must be this, and this entry is 4, 2, 4, 2. There is nothing, so this must be 0. Since this is 0, this must also be 0. So this is how we can actually go back from the Dynkin diagram to Cartan matrices. And uniquely, so basically, if we have two diagrams isomorphic, whichever way you label them, you will get the same Cartan matrix. So as long as your diagram, the Dynkin diagrams are same. Well, so this can be given in theorem. So for each Dynkin diagram or Cartan matrix, there is an irreducible root system having the given diagram as Dynkin diagram. So basically, we do not know whether for a given Cartan matrix or for a given diagram, there is a root system, right, from which it comes. This theorem, again without proof, shows that, yes, if you give any Dynkin diagram or equivalently Cartan matrix, because now we know that they're equivalent, so there is an irreducible root system having the diagram. So basically, for here, if you want irreducible root system, we want this Dynkin diagram to be for each connected. Otherwise, it will not be possible. Okay, so connected Dynkin diagrams. As we have seen that if the root system is not reducible, the Dynkin diagram is disconnected. It has only connected copies. Okay, so this theorem asserts that there is a root system. Well, so we started with G semisimple Lie algebra, H Cartan subalgebra, and then from there we got a root system. From then there, by choosing a basis and by choosing a base and order of the simple roots in the base, we can write a Cartan matrix, and from there we could find a Dynkin diagram. Okay. So basically, we want to classify. We are heading to classification of semisimple Lie algebra. So here, this way, from Cartan matrix to Dynkin diagram, we have seen a bijective correspondence, right? Right now we have seen. And from Cartan matrix to root system, we have also discussed this, okay, in our previous lecture, that Cartan matrix actually defines the root system. So basically, phi 1, phi 2, two root systems, if they give the same Cartan, okay, let's say Cartan matrix M, then phi 1 is isomorphic to phi 2. Okay, and if two systems are already isomorphic, then their Cartan matrices are the same for sure. So there is this one-on-one correspondence also. So we want to find a bridge. So basically, this gap is there. So we don't know whether we have one-on-one correspondence here. So we will now focus on that part. Okay. So this theorem tells us that if G is a simple Lie algebra, then its root system is irreducible. Okay, we are now going back to the simple Lie algebra thing. So if G is a simple Lie algebra, then its root system is irreducible. We know how to find a root system of a simple Lie algebra. and it has a corollary. Okay, so suppose G is not simple but semi-simple. If G is a semi-simple Lie algebra with Cartan subalgebra H, so you fix it, and you get the root system phi out of H. We have also mentioned this result that if G is semi-simple, G is a product of simple ideals, direct sum of simple ideals. So G, suppose it is written in the form of direct sum of simple ideals. So basically you decompose it into simple ideals. Then you have the Cartan inside G. You consider the intersection of H with each of the summands here. Okay, so then this intersection will give you some Hi. Okay, it happens that Hi, this Hi is a Cartan subalgebra of Gi. Okay, so now Gi was simple ideal, so basically it's the simple summand, and Hi is a Cartan algebra inside this, so it has a root system, right? Because semi-simple, simple and Cartan, we have a root system, and suppose we call them phi I. Basically, phi I is the root system of Gi Hi. Okay. Then phi is actually nothing but phi can be written as this. So phi 1 union dot phi k. So okay, this was k. So phi k, fine. So phi can be written as a union of phi 1 up till phi k, where phi I is the root system of these individual Gi Hi, okay, individual components here. And this gives actually a decomposition of phi into irreducible subsystems. Okay, so phi was not irreducible. Anyway, it cannot be irreducible because G is not simple, G is semi-simple. So now we see that phi, if you just construct phi as phi 1 union phi to phi k, you will get the root system of G. So basically, this tells what? If you just classify the irreducible root system, or if you find a bijection between irreducible root system and the simple Lie algebras, okay, then we are done also with the semi-simple case. So then by this one fashion, you can actually find the bijection between semi-simple and all the root systems. So basically, the aim is to classify simple root systems, irreducible root systems, and a bijection of them in bijection between irreducible root system and simple algebras. So this theorem tells us that if G and G dash be simple algebras, then Cartan suppose the Cartan algebra H and H dash with root system phi and phi dash. If phi and phi dash are isomorphic, okay, then G and G dash are also isomorphic. This is called the isomorphism theorem. So basically, it says if you have two simple Lie algebras, G dash, it has a root system phi, G dash has a root system phi dash. Suppose these are isomorphic, okay, then G is isomorphic to G dash. We are doing it for simple, but then again, by this corollary, we can actually generalize this to the semi-simple case. Okay. Well, we started with a simple Lie algebra, okay, and then the root system, right? But we do not know whether for every root system there exists a simple, for every irreducible root system there exists a simple Lie algebra of which the given root system is the root system. So if one phi is given irreducible, let's say irreducible phi, whether there is a simple G, whether there is a simple G whose root system is this phi. So this is the existence theorem. We have not seen it because we always assume that the root systems are coming from some Lie algebras. Okay, so existence can be shown. So basically, if G is semi-simple, H is Cartan subalgebra, you take a root system, you decide a base, and then we can actually choose Hj, okay, from what? From Cartan. So Hj's, they are from Cartan, okay, such that alpha I H j is alpha I alpha j, which is nothing but 2 alpha I alpha j by alpha j. And we can also choose xi yi from L alpha I and L minus alpha I such that hi equal to xi yi. Okay, so basically xi y must be inside L alpha I plus L alpha I plus minus alpha I, so L0. Okay, L0 is nothing but the Cartan. So clearly we can find xi y such that hi equal to xi yi. Well, so the idea is the following. So if you start with a simple semi-simple Lie algebra, so G is suppose a semi-simple Lie algebra, and you look at the root system and check for properties. What are the properties satisfied by the roots? Then artificially we can just consider some. So inside a root system we can consider some generators. We'll see what are they, and force them to satisfy such relations which are expected, and check whether we get a semi-simple Lie algebra. That's all. So basically, if G is a semi-simple Lie algebra here, okay, then G is generated by all these xi, yi, hi, which are introduced here. Okay, so for G semi-simple, we could find xi, yi in L alpha I, L minus alpha I, and such that xi, yi, hi. So with all this notation, we are writing this. So if G is semi-simple, then G is generated by all these generators. So G is generated by means G is generated as a Lie algebra by all these elements, 1 less equal to I less than equal to L. So there are 3 L generators, and which satisfy this. Okay, so one can check that these are the properties S1, S2, S3, and Sij plus, Sij minus. Okay, these are the properties which are satisfied by the element, by these xy, by the xy, xi, yi, hi from the root spaces. So like L alpha I, L alpha j. Okay, so now if we try to artificially, I will basically construct some Lie algebra. So basically we give them these generators and ask them to satisfy all these relations, whether we get one suitable or expected Lie algebra. So that is given by Sayre's theorem. So it says, so basically we are starting with a root system phi, and we want to construct a semi-simple Lie algebra of which this is the root system. This phi is the root system. Well, so we must start with a root system phi. Okay, and once we have a phi, we can choose a base alpha 1, alpha 2 till alpha L, and now generate the Lie algebra by these 3 L generators xi, yi, hi. Okay, and force them to satisfy these relations S1, S2, S3, Sij plus, Sij minus. Okay, so you construct the Lie algebra generated by xi, yi, hi, 3 L generators, such that all these S1, S2, S3, Sij plus, Sij minus are satisfied by this. The relations are satisfied by this generator. So basically, this is kind of generator relation description. So then, since you are generating a Lie algebra, the theorem says that Lie algebra, whatever you get from the generators, is a finite dimensional semi-simple Lie algebra. So both finite dimensional and semi-simple Lie algebra, which are where the Cartan subalgebra is generated by these elements hi. Okay, and it has the corresponding root systems phi. So basically, Sayre's theorem says that basically this is the existence theorem. So if you start with a root system phi, you can construct a Lie algebra L which is finite dimensional, semi-simple, and whose root system is phi. That's all. So basically, this tells what? So if phi is a root system and semi-simple Lie algebra, so there is a by correspondence. So basically, if there are two semi-simple Lie algebra which are isomorphic, then their root system are isomorphic, of course. And so basically, whether there is a bijection, we want to ask. So if phi is a root system, we can actually find one semi-simple Lie algebra. Okay, at least this is the existence theorem. So basically, for every phi, for every root system, we can go back to the semi-simple Lie algebra, or we can go forward like phi, then the Cartan matrix, and then the Dynkin diagram, right? So basically, the final classification is of semi-simple Lie algebra in terms of, or simple Lie algebras in terms of Dynkin diagram, which will come on. So this is So let me just go back to this and talk about here. So linking diagram, there is a bijection between Cartan matrices and there is a bijection between root systems. Now from root system to semi-simple, we have seen a bijection, right? And therefore, classifying the semi-simple Lie algebras is equivalent to classifying linking diagrams. But if we want to just consider connected linking diagrams, we are necessarily classifying the simple Lie algebras. That's all. This is the outcome. So this is the classification result. So now we know that, so there is a bijection, but we still don't know, given, no, this is fine, okay. Well, so the motivation here, so basically suppose given a Lie algebra G, we want to study their representations or modules, let's say G mod, okay, G modules. We ask whether there is an associative algebra, okay, and then the modules on A modules, basically we can say A modules and G modules, okay. So whether there is an associative algebra for which the representative of G and representative A both are same, in the sense that there is a bijection between G modules and A modules. So this associative algebra exists, and that is the universal enveloping algebra, which is denoted as UG. We'll see here. So universal enveloping algebra of G, which means what? This is one associative algebra whose representative theory is same as the representative theory of the Lie algebra, the original Lie algebra. Okay, how to construct? There is some construction. We call T0 to be the field. We can just call C. Now we can take any algebraic closed and Cartesian field. We call T1 to be just G and T2 to be G tensor G as vector spaces. And then Tn, G tensor G n times. So Tn is a vector space. And then dimension of Tn clearly is dimension G whole power n. So then we can construct an algebra which is called the tensor algebra. So basically the vector space, as vector space, it is T0 direct sum T1, direct sum T2, and so on. Okay. And from Tm to T, from Tm cross Tn to Tm plus n, we can give this product structure. So in Tm, x1 tensor tensor xm. Okay. So tensor of all these m elements, this is a simple tensor. So dot y1 till yn. Tensor product. So these type of tensors, they form basis of the vector space Tm and Tn. Therefore, if we define the product here, we can extend it linearly to all of Tm tensor, Tm times Tn. Okay. So this dot is given by just kind of amalgamation, just writing one after the other, x1 tensor xm and then tensor yn tensor yn. So if we extend this linearly to all of T, then actually Tg with this dot, so this dot becomes an associative algebra, and this is called the universal enveloping. Sorry, this is called the tensor algebra over G. Okay, let me just go to the next slide. Yeah. So important observation that one belongs to, so identity belongs to T0. Yes, because T0 is just the field and element. And now if I consider the ideal generated by x tensor y minus y tensor x minus xy. So this ideal, actually we want this to be the two-sided ideal generated by this, not just two-sided ideal generated by this, all these elements. Okay. So this is ideal, and therefore we can consider the quotient Tg mod I and denote it. So this is definition UG. This is called the universal enveloping algebra. So basically, universal enveloping algebra is nothing but the quotient of the tensor algebra by this ideal x tensor y minus y tensor. So ideal generated by all these elements. So for example, if we take G to be the abelian Lie algebra, okay, with dimension G equal to, let's say, D, then UG is what? UG is the tensor algebra of G over x tensor y minus y tensor x minus bracket of xy, but since this is abelian, bracket of xy is 0, and therefore you get this quotient Tg tensor algebra of G over x tensor y minus y tensor. So basically all the tensors here becomes all the simple tensors So basically x tensor y becomes y tensor x. Okay. So this becomes, the product here becomes abelian, right? And therefore UG becomes an abelian algebra, so commutative algebra. Okay. And so suppose if dimension of G is D, write G to be, so span of, let's say these are the basis element x1 up till xd. Then what is G? This G becomes just C x1 xd is the polynomial algebra in D elements. So basically these D elements are the basis elements for G. Okay. Because this becomes abelian, this is obvious. Well, so we had G, and then T1 was also G. So we have the obvious map. And then T1 is a direct summand of TG. Okay, so because T1 is the direct summand of TG, we have again one inclusion map. And then from TG to UG, there is a map. This is the quotient map, right? Because UG is a quotient of TG. And so therefore from G to UG, you get a map, you call it sigma G to UG. Okay. And then this associative, so okay, we don't have time. So UG has this universal property. What is the universal property? Okay, so UG is here and G is here and GLV is here. So basically, if you have any representation of G, so basically rho G to some GLV, if you have any representation rho, that representation factors through this particular map sigma, which we wrote here, this particular map sigma. Okay, so basically for any representation given here, there exists a phi, which is an associative algebra map, phi from UG to GLV, such that rho equal to phi compose sigma. Okay. And since this is GLV, this phi is actually representation of this associative algebra. So in that sense, the UG modules, so the representations of UG are in bijective correspondence with representations of G. And this such phi is actually unique. There exists unique phi such that this also. Okay. And the biggest theorem in for universal algebra is the following. So basically it says, if you write a basis, let's say xi, I belong to I. So here we are not assuming that the Lie algebra is finite dimensional. So we write a basis, okay, and I is any indexing set. And suppose this I is totally ordered by this symbol, okay. Then if you also assume that sigma xi, the sigma basis elements are yi's are in UG, then all these monomials actually for all n bigger equal to 0, ri bigger equal to 0, and for all I1, I2, In inside I, they form a basis for UG. This is a non-trivial result. It may look trivial, but it's not not a trivial result. So this says we can actually write a basis for UG, and the basis looks so obvious. Okay, this is the PBW theorem. There are some corollaries to this. So basically, then sigma map, which we are talking about, sigma G to G, G to UG becomes actually injective. And also, so if you just consider sigma of G inside this, okay, inside this, then sigma G is actually sub-algebra of the Lie algebra of UG, right? So in every Lie algebra, so G was arbitrary. So every Lie algebra is actually a Lie sub-algebra of the Lie algebra of an associative algebra, right? From associative algebra, we know this is just the bracket is defined by A dot B minus B dot A. B dot A. Okay. So in that sense, in this associative algebra is also Lie algebra. So actually, so since these lectures are in Harish-Chandra series, I wanted to present something where we can at least take the name of Harish-Chandra. So for that, so probably we don't have time. Shall we? Can I take 2 or 3 more minutes, Devendra?
Yeah, sure. Go ahead.
Okay, then may not be 2, maybe 5. So basically, what about? So basically, I wanted to reach this Harish-Chandra's theorem. Okay. So we know that H is a Cartan subalgebra. Suppose inside H in, let's say, G. Okay, G is the semisimple Lie algebra and H is the Cartan subalgebra. Okay, then there is something called I lambda. So basically, if you take lambda mu belong to H star. Okay, then there is something called chi lambda, and so basically chi lambda and chi mu. So what are they? They come from this. So basically, I want to just go over this construction and also define these weights. So if G is semisimple and V is a module over G, okay, then V is a direct sum of V lambdas, where V lambdas are this defined by this. V belong to V, such that HV equal to lambda HV for all H in H. So basically, V is actually a simultaneous eigenvector for H. So if V lambda is non-zero, V lambda can be zero as well. But V lambda, if it is non-zero, then lambda is called a weight for weight for V. And V lambda, the space is called weight space, and lambda is called the weight actually. And we do not need this definition of positive roots anyway. So what are maximal vectors? Maximal vectors are those. So basically, suppose V plus inside V, of course, inside the module. If G alpha V for alpha bigger than 0, so I don't want to use this notation. I can just say for all alpha simple. For all alpha simple. For all alpha simple. So before that, we have to fix a basis for all alpha simple. Okay. So for all alpha simple, if G alpha, this is coming from the root space decomposition. If G alpha V is 0, then V plus is called maximal vector. Okay. And then we can also consider this. Okay. So H direct sum G alpha positive. Okay, so alpha positive maybe we need. So what is when a root alpha is called positive, or one root beta is called positive? So when beta can be written as summation ki alpha I, where all ki's are positive. Okay, so then beta is called positive. So then if you consider this, this is actually subalgebra B, which is direct sum of H and the product of direct sum of G alphas, where alpha is a positive root. Okay, this is B, and then D lambda, call this to be span of V lambda, where V plus actually. There is no V lambda. Okay. So D lambda, you just take span of V plus. Where is V plus? V plus is in G lambda. V plus belongs to G. No, V plus. Sorry, why G lambda? V plus belongs to just V lambda, that's all. Okay. So V plus in V lambda, which is a maximal vector, we can, so basically this is a one-dimensional space, D lambda. And then on this D lambda, this B actually acts. Why? Because H acts on V lambda diagonally, and G alpha is actually gives 0. G alpha V plus. This is written here. Okay. So we have an action of B on D lambda. Since B is a Lie algebra, Lie subalgebra of G, which means B is also a Lie algebra. So D lambda becomes a module over B, but we know that this is also a module over universal enveloping algebra itself, right? So then UB, so D lambda is a module over UB associated. There is an associative action on D lambda, and UG. So basically, UB is a subalgebra of UG. Therefore, UB also has an action on UG. Okay, and therefore we can take this tensor product UG tensor UB over tensor D lambda over UB. Okay, so this is called Z lambda. Okay, and then if we consider the center of universal enveloping algebra, okay, this acts on Z lambda, this space Z lambda. Okay, this action is a scalar action. Okay, anyway, so from this action we can actually find, a chi lambda, which is scalar map. Because this action is given by this is actually scalar action, we can actually find kind of lambda again. So this is called chi lambda, which is called the central character, because this is going from the center and landing at the scalar field. Well, so if these are central characters, so not all chi lambdas are different for different lambdas. So basically, if we take lambda mu in H star, okay, then they are called linked. They are called linked. We actually, the notation is this: lambda linked to mu. if lambda plus delta and mu plus delta, they are conjugate with respect to the Weyl group. So Weyl group acts on all of this. Okay, if somehow they are conjugate under W, they are called linked. In this here lambda here delta is the sum of half sum of positive roots. So basically we know positive roots, you collect all the positive roots, you add them up and then divided by 2. That is delta. Okay, so with this all this notation, the Harish-Chandra theorem tells us that if lambda mu belong to H star, then chi lambda and chi mu, they are same if and only if lambda and mu are actually linked. And it has several applications in so calculating the character formulas and so on. So basically I want to stop now. It's already past 5.
Is there any special name of this theorem?
So Harish-Chandra theorem actually attributed to Harish-Chandra. I don't exactly
There might be
the origin of
hundreds of theorem by Harish-Chandra.
What theorem?
There might be hundreds of theorems by Harish-Chandra.
Okay.
So any
So
special
this is Harish-Chandra theorem for central
caption?
character, maybe.
Okay.
For central characters. Sorry, I did not have too much time to explain all these central characters. No, it is central characters. Okay, that's all from my side.
Okay, thanks, Samir, for wonderful course on Lie algebra and 2 talks on the.
Thank you, Devendra.
So, if someone in the audience has any questions for you, Professor Muruganandam, are you there? Perhaps he is not aware. Okay, then if there is no more questions, so we will thank Samir again.
Okay, then.
And we will try to close it.
Yeah.
Send me the slide sometime, maybe.
Yeah, that I will try.
Okay, then thanks. We will stop
Okay, then.
this session.
Thanks. Yeah.
Bye. Good night.
Bye.